Okay, so yesterday we saw that the generating function of correlation functions for operators in the conformal field theory is equal to the partition function of the gravity theory with given boundary values for at the boundary of AdS. So this at the boundary is equal to phi naught of x. Okay. Now this will be approximated as the classical action times quantum corrections. Okay. Now the classical action is basically the classical action in the full string theory, and it has an expansion in terms of the classical gravity action plus alpha prime corrections. Okay. And the classical gravity action, we saw that it has an overall factor of n squared, and then it depends on all the supergravity fields. Okay. Where here we can think of AdS cross S5 as having radius equal to 1. So any computation that we do using just the leading gravity approximation, using the 10-dimensional supergravity approximation, will always give us results which are proportional to n squared. They'll depend only on n and not on alpha prime. Including alpha prime corrections, we get the 1 over. So alpha prime corrections will be corrections to this, which are of order 1 over square root of g squared n. Okay. Okay, so now let's look at one example a little more explicitly. Let's suppose that on the bulk we have a scalar field. So the integral square root of g d phi squared plus m squared phi squared. Okay, so we have this bulk scalar field. Here we can put the radius of AdS here. Okay, so now we can write this a little more explicitly. So we can choose the metric. We are going to choose the metric ds squared equal to dc squared plus dx squared over c squared. Let's imagine we are in 4 Euclidean dimensions for the moment. So this is Euclidean AdS, and so this is the metric. So we can rewrite the action as dc dx over c to the 5th times. Here we have an inverse metric, so we have d squared. Now this is an ordinary derivative, so maybe let's denote this one differently. So this is the usual plus m squared r squared phi squared. Okay. So this is the classical action. In the bulk, there will be corrections to this action, which will be of order phi cubed, like the interactions from the gravitational action. But let's first consider this quadratic term, and then we'll discuss the interactions. So what we need to do is we need to solve the sort of wave equation with given boundary conditions. So the wave equation will give us something like c cubed dc 1 over c cubed dc of phi. So this is just the c derivative. And then we have some spatial derivatives, but there we just Fourier transform. And so we Fourier transform in the x directions. So p here, we have 4 components of the momentum. And then we have minus m r squared phi equal to 0. Okay? So we need to solve this equation with some boundary conditions at the boundary of AdS. Okay? Now let's try to understand a little bit the solutions of this equation. Well, this is an equation that can be solved exactly in terms of Bessel functions and so on. We are not, so it can be. It's an equation that you can solve, but for what we are going to do, we don't really need to solve the full equation. All we need to analyze is we need to understand what happens when c is small. So what happens when c is near 0? And in this case, we can. Well, we see that this term. Well, normally when you analyze c equal to 0 is a sort of singular point in this equation because you have all these powers of 1 over c here. So when you analyze an equation near a singular point, you can approximate it by some power. C to the alpha. And now you can insert this power here, keep the largest powers, the most divergent powers of C, and this will give you an equation for alpha. Okay, so you put it in here, you will get an equation which is alpha from the first derivative, then you get an alpha minus 4 from when you take this derivative, and then from this term we get minus mr squared equal to 0, and well, this term is higher power of C, so will not contribute relative to this term, so this is we get this equation for alpha, and which has two solutions, alpha plus and minus, so a big alpha and a small alpha, which is square root of 4 plus m squared r squared. Okay. Now we see that one of these solutions So for the moment, let's assume the mass is positive. So the alpha minus solution will be such that phi diverges near the boundary, and the alpha plus solution will be such that phi goes to 0 at the boundary. Okay. So if this is equal to 0 and this is C bigger than 0, and we are approaching the boundary, so one solution decreases. This is the solution with alpha plus, and the other solution goes to infinity. This is the solution with alpha minus. So we are going to be interested in putting boundary conditions for this non-normalizable solution. So this solution is not normalizable. If we were to consider this solution and try to compute the action or the norm, we'll get infinity. Okay. But anyway, so here when we were talking about boundary conditions in the beginning, we said, well, we put some Dirichlet boundary conditions for the scalar field. But really, what we should be doing is putting some boundary conditions for this field, that picks out the solution. Now, equivalently, what we could say is, well, we have this quantity that really goes to infinity. So let's not go all the way to the boundary in AdS. Let's just pick some boundary which is at C equal to epsilon, and then in the end, we'll take epsilon going to 0. Okay. So now we are going to put an ordinary Dirichlet boundary condition at epsilon. So we will say that phi of p C at C equal to epsilon is going to be some phi naught of x. Now if we just put the boundary condition like this, as we start removing the regulator, you'll see that if we keep the amplitude of the field fixed here and we move this up to here, then we'll get another solution that will be different. Okay. But the objective of any regularization is that you should change here the regularized value of phi in such a way that the solution here in the interior remains constant as you take the regulator away. Right. So that's what we always demand when we regularize some quantity. So here it's clear what we need to do. So we need to change the here in the same way that this non-normalizable solution changes. So we should put here some epsilon to the alpha minus. And so now we put this boundary condition. And you see that now as if we keep phi naught, so this is the normalized value of phi naught of the boundary condition. So if we keep phi naught fixed, we'll be able to remove the cutoff, so we'll be able to set epsilon equal to 0, and the solution will remain, we'll have a smooth limit in the interior. Okay? So that's what we would like to do. Now, the fact that we have to do this implies that there will be a non-trivial, well, in the end we'll have, so remember that phi naught r is the renormalized value that will appear in here. Okay, so and eventually we'll compute correlation functions by taking derivatives with respect to this. Okay. Now what we would like to derive is I'd like to derive for you now the relationship between the conformal dimension and the mass of the field. So in order to do that, what we need to understand is how this correlation function will change under rescalings of coordinates. Okay. Now, if we do the scaling of coordinates x and c going to lambda c, so under this kind of rescaling, the original field, so that was a coordinate transformation, so the original field phi is just a scalar field, so it doesn't get multiplied by any factor. It's just an ordinary scalar field. This has sort of no dimensions. This has dimensions of length. So this phi naught r has the dimensions of phi naught r are equal in sort of energy dimensions. Is equal to alpha minus. Okay. So okay. Now, if we come back to this expression, so this whole thing should be dimensionless. If phi naught has dimension alpha minus, then what should be the dimension of phi, of O? Well, there should be a minus alpha minus to cancel this dependence, but then there is an integral d for x, and that adds 4 to this dimension. Okay? So the dimension is 4 minus alpha minus, and if we remember what alpha minus is, we see that 4 minus alpha minus is just alpha plus. Now this is by definition the quantity we call delta, and alpha plus is, well, 2 plus square root of 4 plus m r squared. Okay? So that's the formula that we promised. Okay? So now let's try to understand some features of this formula. Well, first of all, if the mass is positive, then we see that when we turn on this perturbation, the solution inside AdS, with this perturbation turned on, will be a solution that grows as you approach the boundary. Okay? Now, a very remember that scale transformations with scale coordinates in this way. So doing a scale transformation in the field theory moves you in the c direction, and it moves you in the c direction in the following direction. If you go to longer distances in the x direction, you are going to long distances in the c direction. Okay, so that means that this region, so the region of large c, that is related somehow to the infrared region of the field theory, while the region of small c will be related to the UV region of the field theory. And so this is the fact that as you go away from the boundary, you go to the infrared and so on, is very important. So almost everything in AdS CFT depends on this fact. Now, okay. So here we saw that for a positive mass, the scalar field, this solution grows in the infrared, in the ultraviolet, and that agrees with the fact that this conformal dimension is bigger than 4, and so this is a so-called irrelevant deformation. So this naming of irrelevant or relevant is saying how the perturbation behaves when you go to the infrared. So if you add this perturbation to the Lagrangian, as you go to the infrared, it will become less important, right? So that's the definition. This is the definition of an irrelevant perturbation in the field theory. And the opposite thing, so delta smaller than 4, that's a relevant perturbation. Okay? And that would correspond, in order to have delta less than 4, what you need is to have here mass less than 0. So this will happen when m squared is less than 0. Okay? And if m is equal to 0, then delta is equal to 4, and you have a marginal perturbation. Now, you have something that is marginal to first order. In order to see whether it's marginal to all orders, you need to compute the terms in the Lagrangian that we neglected. So you need to know whether here there is, for example, a phi cubed term or not. Okay? So an example of a marginal deformation is the zero mode of the dilaton, that has an action with no term here, so Defy squared, and we can change the value of the dilaton, and that's an exactly marginal deformation. Okay, now you might be surprised by the fact that we have some negative mass scalars. So these are tachyons. And this might worry you a bit because having a tachyon is normally a sign of some instability. Okay. Now, it turns out that if the tachyons are not too tachyonic, so that is, if m squared r squared is bigger or equal than -4, so that the argument of that square root is positive or 0, then these are okay tachyons. So these are okay. These negative masses are. And what happens is that even though naively you think you have a tachyon, since in AdS you will have some boundary conditions that will impose that the field should vanish at the boundary, then that will force this field to have some variation in the internal directions. So sorry. It will be forced to vary in the spatial directions of AdS, and that will give this field some kinetic energy, okay? That will add to the negative potential energy. So here we'll get some negative potential energy from this term, but we'll get some positive kinetic energy from demanding that the field obeys the proper boundary conditions, that is, that goes to 0 appropriately fast at the boundaries. And it turns out that the positive kinetic energy is always bigger than this negative potential energy. And so it turns out that the energies of these particles in AdS are always positive. Okay. Yeah. Okay. So here I guess I omitted to say something. This remark was a remark for. Okay, I need to say two things. So let me first make contact to what I said before for relevant deformation. So if we have the theorem R4 and we turn on a relevant deformation. So for a relevant deformation, there will be two rates of decay here. One which is fast, very fast, and the other one which is not so fast. Okay. So one will decay more slowly, and the other one not so much faster. The boundary condition, we are always going to put it on the one that decays more slowly. Okay? Well, not always, sometimes on the other one, but let's for the moment ignore that possibility. So on one of these two, let's say. But regardless of which one we choose, it turns out that as you go to the interior, this perturbation grows, and so it'll eventually become non-linear, and you'll really have to solve the full equations. And so if you turn on this perturbation, you'll have to work a little harder to find what happens here in the infrared. Okay? That's when you turn on the perturbation. Okay. Now, for all these fields, whether they are tachyonic or not, or any fields, you can consider physical excitations in AdS. That is, for example, you can consider AdS in global coordinates, and so we'll have some boundary, and then you consider some physical excitation, so some particle that lives in AdS. Now, these particles obey the boundary conditions that the fields here should vanish at the boundary, okay? Because these are particles that are excitations of the system that exist without the need of adding any perturbation to the Lagrangian. So there are two things we can do. We can add a particle to the theory, or we can perturb the boundary conditions. If we are going to be talking about a fixed theory, like n equal to 4 young males on S3, and we want to consider excitations of that theory, we need to consider here excitations, and we need to impose boundary conditions here equal to 0, so that we really have the original Lagrangian. We are not changing the Lagrangian. We have the original Lagrangian, but we are considering physical excitations. So in that case, all these particles are forced to have wave functions that vanish at the boundary, including these tachyons. So these tachyons will have to have boundary conditions that they go sufficiently fast to 0 near the boundaries. And that's what forced them to vary and so on. I hope I answered your question. Okay. Okay, so Now, well, so I set this. So now, as you including here some corrections, will boil down to considering these kinds. So you consider multiple insertions, and you'll end up having to consider this kind of Feynman diagrams, as I think we discussed yesterday. Okay. Are there any questions? Yes. 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 Well, I would have said that we derived it here, but yeah, so it's the dependence that you introduced through the regulator. So naively, it didn't have any dependence, any scaling dependence, but due to the fact that we need to regularize it, it got some scaling dependence. Okay. Well, by naive is that the naive you would guess from the bulk point of view. Yes. Mm-hmm. You put the field is a scalar field, so when the reparametrization it doesn't change. But due to the fact that we really need to regulate this way, and so it's really the fact that when we, I mean, this is a completely classical effect. So this is a feature of the classical solutions in AdS. In order to define things properly, we need to make these kinds of rescalings. So in other words, the dimension of the operator is related to how solutions of the classical action behave when you are close to the boundary. So how they behave is telling you, well, how you should rescale the boundary conditions. And that's related to the scaling dimensions of the operator. Now, this is sort of a quick way to derive it. You could have ignored this if you don't like it, and you can, well, impose this condition and actually compute the two-point function, which I didn't compute here. But so it's one more step here. In order to compute the two-point function, you have to really solve that equation with given boundary conditions, and then you put it back into the action. And what you'll find is that the action will have the form that I think I wrote yesterday, with delta equals this value. Mm-hmm. Okay. So no. Now, so I'm now going to say various remarks, not connected with each other, but various points. So when we were solving this equation, for example, that equation, we had one boundary condition at c equal to 0. And then we'll need to say something about the behavior of the solution at infinity. So we'll have to impose that, for example, c that the solution phi goes to 0 when c goes to infinity. Okay. So that's this condition is basically saying that the solution is regular in the interior of AdS. More specifically, it's saying that when we are more properly. So if we have these coordinates, so where we have R4 and C, we can choose a coordinate transformation to some kind of global coordinates for the Euclidean AdS, where the boundary now is an S4, and we have some radial direction. And the change of coordinates can be found very easily by thinking of AdS in terms of this hyperboloid that we discussed before, and choosing different coordinates for that hyperboloid. And if you do that, then this point c equal to infinity is really a point here on the boundary. This is the point c equal to infinity, and so and surfaces of constant c in these coordinates correspond to surfaces that basically do something like this in these other coordinates. Okay. So when we are putting some boundary conditions on the boundary, we are putting some boundary conditions, and when we put this condition, we are just saying that we don't have a strong divergence here near the boundary. Now, in general, if you are conceptually, if you have some boundary conditions at the boundary, and that come from, let's say, you have n equal to 4 Young mills, and you perturb it by, let's say, a relevant deformation. When you solve these equations, you will need to impose a condition here in the infrared that basically saying that the solution is non-singular. So the solution should be non-singular, and this will effectively impose some boundary conditions here in the infrared, and then you'll need to find the solution of the equation. Okay. So, I mean, it's a second-order equation, so you need two boundary conditions, and so the boundary condition in the infrared comes from demanding that the solution is non-singular. Now, this non-singular should be non-singular in the full string theory. So it might be that from the gravity point of view it's singular, but that singularity can be interpreted as the presence of some brane, or it has some interpretation. So the only singularities that are allowed are those that have some interpretation. If they don't have a good interpretation, then they are not allowed. Okay. Now you might be tempted to say, oh well, string theory will eventually resolve all singularities, so I don't need to impose any condition, I don't care. But this clearly will lead you to problems. And so, for example, if you have AdS in global coordinates, now this is a spatial section of AdS, and then we have the time direction. So solution you can consider is, for example, a black hole here. Okay, so a positive mass Schwarzschild solution. Now you can say, okay, I now choose to have a negative mass Schwarzschild solution, and that solution has a singularity here at the origin. Okay, and you can say, well, string theory will resolve the singularity. I mean, I don't care. I want to consider these solutions and do something. But then, well, there is the problem that the energy in the field theory, this was a supersymmetric field theory, so the energy was supposed to be bounded below, and this gives you negative energy. So that is raising for you some questions. But there is also another property, bad property for negative mass objects, whether they are singular or not. Actually, this is okay. One bad property is that if you take a light like geodesics through the bulk from here to some point over here, it turns out that the time it takes for a light signal to propagate through the bulk is actually less than the time it takes for a signal to propagate through the boundary. Okay? So this kind of bulk solution will lead to some acausal effects in the boundary theory. Okay? So if you have an ordinary causal boundary theory, you should never have a configuration where, at least outside some region, I don't care about this region, but if outside this region you have negative mass Schwarzschild solution, then you have this bad property. Okay, so that's one sort of interesting point that was made about this. So in any case, it's only some singularities that will be resolved by string theory, and some others you expect them not to be resolved. Okay. Now, there is some discussion of whether the conformal group has a very special representation, which is the representation with conformal weight equal to 1. So basically the field trace phi I. So if you have an operator with conformal dimension equal to 1, it turns out that just purely from the point of view of conformal symmetry, you can show that this is a field that this operator obeys the massless wave equation in 4 dimensions. Okay? So it obeys one more constraint than the constraints that are obeyed by ordinary operators. Okay? So now this is not surprising, since this field is just a U1 inside UN, and it's just a free field, so it definitely will obey the massless equation. Okay? Now, since it's obeying the massless equation in 4 dimensions, it has sort of less degrees of freedom than the other operators. Okay? So, in other words, for the other operators, we have that they don't obey any condition in 4 dimensions, but you need to obey an equation in 5 dimensions. Okay? In this way, you have the same sort of counting of number of variables. So you are in the interior, the theory. So all computations will always be on shell. You will be obeying the equations, but here the operators are not obeying any particular equation. In this case, this operator is obeying some equation. So in the bulk, it will have less sort of states. In particular, among its descendants, it will have less states, and so this cannot correspond to bulk mode. So an operator related to this is the operator trace of nu squared. So that's again the U1 field strength. And so these operators correspond to some topological modes in the interior. So for example, basically if there is a term in the action, so BNS wedge H Ramon wedge F5, this is a term in the 10-dimensional supergravity action. On S5, this will reduce to, this will give a factor of n, and in 5 dimensions, this gives an integral over 5 dimensions of this quantity. Now, the full action contains other terms with more derivatives, like h square ns or h square Ramon. But let's say at long distances, this term will be more important. And well, anyhow, another way of saying this is that when we do a Kaluza-Klein decomposition, there will be one particular mode, which is the mode that, which is the mode that will correspond basically to this massless field. So let's for the moment ignore this at long distances, and so we see that this action is special because it's a topological action. It doesn't depend on the metric, and if you had fields with this action, they lead to no local degrees of freedom. But if you put a boundary and you impose local boundary conditions, then you'll find that this action leads to a degree of freedom that lives here at the boundary, and on the boundary, this degree of freedom is just a vector field, A mu. Okay, so that's the U1 of the UN. Okay. So, in other words, so everything that lives here in the interior of AdS belongs to the SUN of UN. And only this boundary mode and so on is the U1. Okay? You can say you forget about the U1 and then you have only the SUN. So anything that has to do with the bulk, anything that is a bulk degree of freedom interacts with the rest of the bulk degrees of freedom, and so will be in the SUN of the field theory. So in some sense, the bulk of AdS is dual to SUN, not to UN. Okay. Now, as we were saying, it's very important to understand the physics of this warp factor. So let me say some more things about it. So if you have these spacetimes, of which AdS is an example, where we have a warp factor times dx squared plus dc squared, then as we said, the energies in the field theory, or the sizes in, well, the energies in field theory are measured with respect to derivatives with respect to this time, and are equal to warp factor times the proper energies. Okay. We already seen this formula, okay? So here this factor is 1 over c. So when you go to large values of c, you go to low energies in the field theory. And the same equation is for the size. So the size in the field theory is 1 over the warp factor times the proper size. So in this particular case, this is like this. So what this is saying is that if you have your field theory, let's see what's the best way to draw this. Let me draw it here. Suppose you have your field theory, and you consider particles, the same particle, let's say the same string state or the same object, that let's say has some size, let's say Planck scale, and you can put it here or here or here. So when you put it here very close to the boundary, it would correspond to an object on the boundary theory that has a certain size, okay? And as you put it further and further away from the boundary, so when it's here deeper in the interior, it will correspond to basically the same object, but expanded by some factor, okay? So it will correspond to an object of bigger size, and so on, okay? So here, so size in the boundary theory is related to the position C in the interior. Now, so in particular, the limit when we go near the boundary of AdS corresponds to the ultraviolet region of the field theory, okay? So the ultraviolet of the field theory is equal to C going to 0 or going near the boundary of the AdS. Now, going to very large values of C means, from the point of view of somebody who is in the interior of AdS, to go into very long distances. Because remember, the metric had this form dc over c squared. So if you integrate dc over c at small values of c, you get infinity, okay? So you go to very long distances. So that corresponds to going to the infrared region of the bulk theory, okay? Now here in these diagrams, we're always plotting C, and the way we chose the C variable, it might make you think that in terms of the C variable, if you only compute, I mean, in terms of the coordinate C, it looks like a finite distance, but in terms of proper distance, it's an infinite distance, okay? So this relationship that the UV of the field theory is the same as the infrared or long distances in the bulk theory is called the UV-IR connection, okay? And so divergences, or so many times, like in what we said before, that we do computations, many times we need to regularize here and put a cutoff at c equal to epsilon, and then remove this cutoff. So any computation that we do in AdS with a finite cutoff will be some computation we do on finite volume, and will give us a finite answer. So as we remove epsilon, we tend epsilon to 0, what happens is that the bulk space gets infinite volume, and so there could be some infinities that come from the fact that we have infinite volume. So some long distance infinities. So these long distance infinities are interpreted in the field theory as ultraviolet infinities that we need to regulate in some way. Okay. Okay. So, are there any other questions? Yeah. Yeah. That's when you solve an eigenvalue. So it's important here that we are solving an equation with an inhomogeneous right-hand side, right? So we said that the eigenvalue condition is only when you impose grad square equal to 0, right? And 0 boundary conditions, homogeneous boundary conditions on the two sides, right? So these two boundary conditions on both sides. But if one of them is non-zero, then that's not an eigenvalue equation. Okay? It's not a linear problem. We have some non-zero thing in the right-hand side. Well, yeah, so, okay, maybe I wasn't clear enough. So, we are going to impose, so if you have some ordinary, I don't know, second order differential operator, like d squared phi, right, equal to 0. Here you impose, let's say, phi equal to 0, that's the interior. On the boundary, you say phi equal to, I don't know, some phi naught, okay? So then this will have a solution, right? This will always have a solution, I mean, it will be a straight line like that, right? So you only get the eigenvalues, an eigenvalue equation if you impose that this should be equal to 0. Okay? And then you'll need to quantize the parameters that appear here in order to have the solution. I mean, otherwise you won't have a solution. Is that clear? Yeah. Well, what I was trying to explain is, well, let's start with simplest things first. the UN field theory is basically U1 cross UN, SUN, right? Up to some mod by Cn, but let's ignore this. So the SUN part is all interacting among itself. This is a free part. Now anything that is some bulk mode that lives in the interior of this space will interact with all the other bulk modes through gravity, for example. So all those bulk modes should correspond to SUN, should be dual to this SUN piece. Now you can ask, well, what is this U1? Okay. One point of view is to say, well, the U1 is not there. We should only consider the SUN. However, you can still get the U1 if you focus on this kind of interaction in the Lagrangian. So if you have this type of interaction, if you have this type of action, then this is something that has no degrees of freedom in the bulk, but it leads to 1 degree of freedom in the boundary. Okay, but this is a Chern-Simons action, and as happens in three-dimensional Chern-Simons, you'll get a degree of freedom in the boundary. For that, you need to impose some local boundary conditions here at the boundary. Okay, so you can somehow see this U1 if you consider this term and put local boundary conditions at the boundary of AdS. Well, yeah. I mean, there are other ways of thinking about it. I mean, perhaps the most direct way to understand it is to go back to the full D3 brane. So the full D3 brane is some solution roughly like this, and then what will happen is that there will be. So now we have these terms in the action with F, and then the metric will not be constant on the sphere. So there is a strength here that goes to 0 at infinity and non-zero here. So what this eventually leads to is to the existence of a normalizable mode here in the region that connects the bulk and the boundary. And this normalizable mode gives rise to the gauge fields and the center of mass motion for the whole brane, including its gauge field. And if you ask where this gauge field comes from, well, it comes from this combination of the NSB and H. Okay. Okay. So now, yes. What? Well, it does not propagate because it's related to. So if you had this action in 5 dimensions, they will not have any propagating degree of freedom. Okay. Now, of course, we do not have this action. We have this action plus h squared and so on. And so the proper statement is that you do some kind of Kaluza-Klein decomposition, and so there will be some massive modes coming from h, and this coupling will lead rise to some massive modes, and some sort of massless topological degrees of freedom, which are the same as the one you would have if you didn't have this term. Yes. Oh, that exists on the boundary. That's some boundary term. And so here, when we put some boundary conditions, we'll have to choose some Lagrangian we'll have the value of the coupling for this and so on, which is the normalization of that kinetic term, will depend on the boundary conditions we put, and it's arbitrary. It's not related to the bulk gauge coupling. So that's the fact that you can vary these two couplings independently. If this is causing some confusion, just forget about the U1 and say SUN in theory. It's a simpler statement. SON, then there is no issue. And so what happens in SON? So what happens is that SON, as we said, was some orientifold, where you orientifold, where at the same time you reverse the time directions, the S5. Now, of course, if this now in any orientifold, let's say we do an orientifold in 10 dimensions, then the NSB field will be projected out. Okay? So what happens in this case is that this NSB field doesn't have any indices on the sphere. This is the part of the NSB field that has indices only on AdS, so it will be projected out. Okay, so we'll not have this coupling, so we'll not have this issue with the U1 or anything. And the same happens in SPN. Okay. Okay, so now let's now an interesting operator that we mentioned the first day was this Wilson loop operator. And so you can ask, if you have a Wilson loop, how do you compute its expectation value? So if we have this Wilson loop operator, which is the path order exponential of the integral of A. So now we want to compute the expectation value of this operator. So this is along some curve C. So we have the boundary theory, and here we pick some contour C. And so we ask, well, how do you compute an expectation value? Now, this operator is what appears if you is the phase factor that appears if you consider the propagation of a quark charged, let's say, in the fundamental representation, and you move this quark along this curve. Okay. So you have a quark that describes this curve, and the phase factor is this. Now we said that in general, if we have let's say a quark and let's say an anti-quark, then we'll have a string that goes between the quark and the anti-quark, right? We can think of this string as what's made by the Feynman diagrams of gluons exchange between the quark and the anti-quark. But this is the string of Toft, okay? Did I write this? Yeah. Good. So this is the string of Toft that you made by Feynman diagrams, and what we are saying is that that's the same as the fundamental string, right? And this fundamental string was not constrained to live in the 4 dimensions, but can live in 5 dimensions. So here what you will have is a 2-dimensional worldsheet sigma, sigma 2, which will end on this contour. Okay? And so that will be the shape of the string that that is ending on these quarks. Here, when we draw this diagram in 4 dimensions, we draw this string as going between here and here, and we naively we think of this string as living in 4 dimensions, but in AdS CFT we should think of this string in 5 dimensions. Of course, any property of the string here will have some counterpart in 4 dimensions. So the fact that when you have let's say a quark and an anti-quark, you'll have a string worldsheet that goes that will basically have its shape. Maybe I should first say why the string worldsheet has this shape. So in AdS, all particles are pushed towards the interior. Okay, there is this big gravitational force that pushes everybody to the region where the work factor is very small, right? So here we saw this fact that the energy in the field theory is given by this. So everybody would like to minimize its energy, and that's why sort of everybody is pushed to the interior, right? And that's the same reason why we are pushed to the center of the Earth, because the redshift factor is smaller at the center of the Earth. Okay. But anyway, so we are everything is pushed towards the interior, and in particular, so the string, well, it has to end here on the boundary, but it will try to minimize its energy by going between these 2 boundary points through some trajectory that sort of bends towards the interior. Okay. Now, moving here into the interior corresponds to the string here becoming thicker. So we said that position was related to size. So from the 4-dimensional point of view, we have some object here which is somewhat thickened. Okay. So so that's what we have in this theory. Now, if I ask you, so suppose I separate this by some distance L in the boundary theory, how much does it get thickened in this direction? Can it thicken in this direction by an amount e to the minus L, or by an amount 1 over L, or by L? So a hint is that the theory is conformal invariant. So it can only be L because all other these expressions would require another. So this gets taken by an amount of order L. Okay. Anyhow, and if I were to compute the potential between the quark and the anti-quark, what should I obtain in this theory? So again, the theory is conformal invariant. So what should its L dependence be? The potential has units of energy. So the only thing it can be is 1 over L. Okay. Okay. So now. So how can we compute this potential? Well, we said that in AdS we'll have this solution for a string function that does this, and here is that the expectation value of the Wilson loop to lead in order is just given by the action of the solution. So the same formula that we had for correlation functions. So here now it gives us that this will be the action of the solution, and the action is the Nambu action. So it's the area of that minimal surface, okay, times the tension of the string, okay. So tension of the string goes like 1 over alpha prime, and so this will have a factor of 1 over alpha prime, or square root of g squared Young Mills n. Okay. So that's just that factor of alpha prime, and yeah. Yes. 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 No, yeah, no, I'm not assuming that. All I am assuming is large n. This is the only thing that I am assuming. So we are in the top limit for large n, and the strings we are talking about here are not the strings, well, these strings do not lead to confinement. So this top argument for large n predicts the existence of some string. But it does not tell you that the theory will be confining. And in fact, the conformal field theory cannot be confining. So that's why we had this potential. We will see later what the confining theory should look like in the gravity side. And indeed, if we had a confining theory, this string cannot get very thick. It will have some finite thickness. We'll see how that works. Okay. Well, maybe we can already see it now, before we go on to compute this. So in the case that we have this Meissner effect and so on, what we expect is that this string should have some finite thickness. Okay, so as we separate the quark and the antiquark more, there is some. This is confined to some narrow tube. Okay. So the size of this string is somehow constant. Okay. So what should that mean in AdS, right? So we said that, roughly speaking, size was position in the extra coordinate, or was the value of the redshift factor in the extra coordinate. And so in confining gauge theories, what we will have is that the geometry, first of all, will not be AdS, because AdS is a geometry only for conformal theories. So we have here some dr4. We'll have some coordinate c. If we have a theory, that is almost asymptotically free in the ultraviolet, so here we'll have an almost conformal theory, so almost AdS near the boundary. But when we go to the interior, typically what happens is that the geometry somehow ends. Okay? So there is some end of the geometry, and this end is such that the warp factor is bounded below. So this C goes from C to some C0, and the warp factor at C0 is bigger than 0. And it's bigger than 0 everywhere else in the node. Okay? So this is bigger than 0, and the warp factor is always bigger than this quantity. So that means that if something wants to minimize its potential energy, it will want to sit here. Okay? So everything will be attracted here, and it cannot go further than here, because here the space will end. Now, how the space ends? Well, how much time do I have? Maybe. Well, depending on the example, that end of the space will be different. So in different examples, the space will end in different ways. We'll later probably see one example. And so if you have a string that starts in here, and so let's first consider a quark and an anti-quark that are positioned here. So the string will roughly do something like this. I'm not drawing the time direction, let's say, it's orthogonal to the blackboard. So this is what the string is doing in the special directions. And then as we start separating this quark and anti-quark, the string will want to move deeper in order to minimize its energy, but it cannot move any deeper than this. So there will be some finite size that the string has and some finite tension that are given by what the warp factor is here in this region. Okay? So the tension of the four-dimensional string will be, well, the fundamental string tension times this the warp factor here at the origin. Okay? So that's the tension that the four-dimensional observer will see for this string. And the size of here will be related to the warp factor at the origin. Okay? So that's what we get for confining theory. Okay. Now, so I went to a small detour. I now go back to the evaluation of this Wilson loop. So we need to compute this area. And as most calculations that you actually do in AdS, you'll get that this area is infinite. Okay. Now this area is infinite because we said that the boundary is infinite. So, and this string is going all the way to the boundary, so its area will also be infinite. So the area is infinite, but what you need to do is you need to again regularize, put a boundary that's equal to epsilon, and consider a string that ends on this boundary, and then you'll find that the area will go like, there will be a diversion term that goes like 1 over epsilon, but this divergence is just proportional to the length of the contour C in 4 dimensions. Okay? So this you can think as a renormalization of the mass of the quark. Okay? And then you get some finite, some renormalized area which is finite. Okay? And so if you do this computation for this kind of contour with length here L and length here in the time direction T, which is the kind of contour you need to consider for computing the quark anti-quark potential. So this is the contour C. Then you find that this finite area goes like minus T over L. Okay? And then by the time you multiply by the string tension and you get rid of this factor T, you get that expression for B. And of course there is a minus sign, so the potential is attractive. Okay. Now, this should be compared to the perturbative answer. So if you, this is the result in the gravity answer. So this result is good when chi square n is much bigger than 1. Now, if chi square n is much less than 1, then we can do the result in perturbation theory, and we just get the exchange of a single gluon, and this gives us this kind of potential. Okay? And so it has a different dependence on n, and so it has a different coefficient. This is when Gn is much less than 1. Okay, so well, this is then some calculation that, well, should not be protected by supersymmetry or anything. So it's some calculation that gives a different answer. Now, it turns out that there is a subset of Feynman diagrams that you can consider, which are sort of Feynman diagrams which, well, we basically consist in exchanging between the two sides, but planar. So it's roughly like iterating the one loop, the one gluon exchange, but restricting the ends never to cross each other. Okay. So these are these double lines, and if you do that, then what you get is something that has a square root of Gn, but it has a different numerical coefficient. Now you can do a little better for a circular contour. So if you have a circular contour, then it turns out that so you have the circular contour on the boundary. So this is the boundary, and so in AdS you'll have some wall sheet, and so the value for the Wilson loop expectation value, as for any other contour, does not depend on the size of the contour because of conformal invariance, and is proportional to square root of G square n with some coefficient here, let's say 1. Okay. Again, perturbation theory would give you a similar thing with the square root of G square n. And in this case, again, there is some Feynman diagrams that you can consider, which are these so-called rainbow diagrams, which are basically diagrams of this type, where they always end on this boundary and they never really cross each other. And if you consider these diagrams, again, now you get exactly the right coefficient. Now, there was a paper by Gross and Drucker who explained why here, in this case, you can obtain an exact agreement between gravity and the field theory. So by summing these diagrams, so I should say that by summing these diagrams, you get the full function. So you get some function of G square n that interpolates between the weak coupling result and the strong coupling result. Okay? And the basic idea of why this happens is that if you consider a straight Wilson loop, so some Wilson loop that is completely straight, then this can be thought of as a BPS object. And when you make the conformal transformation that maps this to a cylinder, there is one finite point, which is the point at infinity, that has basically different boundary conditions when you think of it as this straight Wilson loop than when you think of it as circular Wilson loop. And there is some kind of anomaly, and so all the diagrams that really matter are fluids that connect these two sides. And by considering only these kinds of diagrams, they argue that this result is, they argue you could derive this result. Now there is one little detail that I didn't mention, which is that if you consider these strings, really the operator we are computing is not just this, but it's an operator that contains also a coupling to a scalar field in direction I, where the direction I is the direction on the sphere where this string is ending. So when the string ends on the boundary of AdS, the string will be sitting at some point on the S5. Okay? And so that point will determine the direction in SO6 direction, and you put in here that particular direction. Okay. So now let's discuss. So we briefly discussed these confining theories. Let me go back to these confining theories. So this relationship between gravitational theories and quantum field theories is not something that will hold only for conformal field theories. It should hold in principle for all kinds of theories, whether they are conformal or not. Conformal field theories are simpler because they have more symmetries, but they are not necessarily the only theories that will have a dual. So in particular, it's interesting to understand these confining theories, and you can get confining theories in different ways. You can start with n equal to 4 Young-Mills and add some mass for all the scalars, for all the fermions, and that will lead to a mass. well, basically you can add mass for all the fermions. That leads to mass to scalars, and if you understand which kinds of operators you need to turn on to give mass to the fermions, then you'll understand near the boundary of AdS which fields you are turning on, and then you could try to solve the solutions, to solve the equations of supergravity, and then find some geometry, and that geometry will be the dual of just pure Young-Mills. So Young-Mills here with no massive quarks and massive matter. Now that, if you try just to do that, you'll typically get into trouble, because when you try to solve the equations, these fields will diverge and so on. Now, there are some simple examples where you can actually solve the equations, and what's common to all these examples is that you get a confining theory, like n equal to 1 Young-Mills with one supersymmetry and pure Young-Mills. So examples of confining theories people have discussed are, for example, if you have n equal to 1 super Young-Mills with no matter, well, of course, the very well known of n equal to 0 Young-Mills with no matter. So these are examples of confining theories. Now, we don't yet know the AdS duals of these theories. However, what we know is the AdS dual of some theories that are closely connected with those. So, well, vaguely connected maybe, not closely connected. So it is possible to take some well-understood example of an AdS CFT and then turn on some masses or turn on some operators that will lead to some smooth geometry which somehow ends here. And the way it ends could be purely geometrical. So the way a geometry can end, for example, is if, suppose here you have some extra circle in some internal direction, and then what can happen is that when you get to some specific value of the radial direction, this circle just shrinks to 0 size in a smooth way, and in this way the geometry ends at this point. So this is something, for example, that can happen. Or this, instead of a circle, can be an S2 or something more complicated, okay? Or an S3 and so on. So all this will give you examples of confining theories. Yes. 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 Well, n equal to 0 Young-Mills is the theory whose Lagrangian is trace of f squared. Okay. Okay, I'm well, it's conjecture to be confining. Okay. Okay. Yes. Yeah. Well, that's fine. So to the level of, I think it's well. Anyways, it's numerically proven to be confining. Let's see. Okay. Okay, now when you have this end of space, well, one feature that we had is we saw that we would have confining, so the string tension will be finite. And another feature is that if you have some physical particle here, so any particle, now in AdS you can, well, any particle will be pushed here to the bound to this region of smaller work factor, but it cannot be pushed further than this. And so we have some minimum energy, okay? In AdS, you can decrease the energy of the particle arbitrarily by moving it further and further in the c direction, okay? But here you cannot decrease it further than a certain amount, and what that means is that the theory will have some mass gap. So there will be some mass. All the masses of the particles will be bigger than 0, which is bigger than 0, and so the theory will have a mass gap. So that's also a feature that we expect in confining theories. So in particular, there will be a lowest energy particle that will correspond to some supergravity mode with some wave function that will be localized near this region. And that will be the lowest energy excitation, so that will be the sort of lowest mass blue ball. Okay? And then other particles are other glue balls of this confining theory. Yeah, so the reason there is a mass gap is basically because there is a bound in the warp factor. The warp factor cannot be smaller than something, okay? And so if you have any particle, it will be attracted to this region, but it cannot decrease its energy arbitrarily. I mean, arbitrarily have some minimum energy.
How do I know that I cannot have an excitation?
Yes. Okay, so the reason is that, yeah, so you can say, well, why can I mean, you had all these massless modes in 5 dimensions, so why can't I have a massless mode in four dimensions? So the reason is that any particle that lives here will want to, is attracted to this region, and so its wave function will be forced to vary a little bit in this direction. And this will give it some energy from the 4-dimensional point of view. So that's the reason that from the 4-dimensional point of view, all particles will be massive. We can state this a little more formally by writing down the same wave equation we had before in a space that somehow ends here. And in such a space, that scalar wave equation will always have a positive spectrum. Now, it could happen that there are some massless degrees of freedom that are due to some special symmetries of the solution and so on. So if you add some brane here, for example, it might happen that this brane has extra massless degrees of freedom living there, or well, but those are, well, that could happen. So you could have a confining theory that in addition is coupled to some other theory, and in the end you have some massless degrees of freedom. Like in real, if you have a QCD and we add quarks here, so if we add here some massless quarks, then we will have the massless pions, right? And well, we expect them to be some massless particles that live in this geometry. But those will be somewhat more special. They will depend on some other features of the solution. So far I've been trying to describe the general situation. There might be a small number of massless particles here that are due to some special symmetry. Okay, so that's one generic feature. The other generic feature that we are going to find in all of these confining examples is what happens as you raise the temperature. So when the temperature, when you raise the temperature, then if the temperatures are low enough, so when you start having some excitations of all these massive particles that live here near this infrared region. But if you raise the temperature enough, what will be convenient, so for some temperature above some critical temperature, what will be convenient is to replace this whole region of the geometry by some black hole horizon, okay? And so there will be this transition between having the original geometry and having a black brane, okay? Now once you have a black brane, so one feature you have is that the string can just end on the black hole, and so you will not have confinement anymore. So this will be, at TC, we have a deconfinement transition. Okay. So that is a generic feature of all the solutions, these confining solutions. Okay, so now let me talk about one specific example. So this is perhaps not it's sort of the simplest example that illustrates these points, but well, so the simplest example will be to consider, instead of 3+1 dimensional theory, consider a 2+1 dimensional theory that will be confining. And this 2+1 dimensional theory will be the 3+1 dimensional Yang-Mills theory, n equal to 4 Yang-Mills, super Yang-Mills that we've been discussing. But we take this theory and we put it on a space which is R2,1 cross S1. Okay? And we put anti-periodic boundary conditions on this S1. Okay? So at low energies, So if we consider n equal to 4 Young-Mills theory on this space and at low energies, we find some massless excitations, which will be the 3-dimensional gauge bosons, the 2 plus 1-dimensional gauge bosons, and well, the scalar fields will be massless, but the fermions are not going to be there, so the fermions are going to be massive. But the interactions of these fermions with the interactions of the fermions with the gauge bosons will give some mass to the gauge bosons, like Fernando was discussing for the Higgs field. But so similarly here we'll get some mass, which will be order of the chi square n. So if chi square n is large, so we'll also chi square n times the mass of the fermions. So I should have said that the mass of the fermions is of order 1 over r. R is the radius of this direction. Okay. So we'll get masses of this type. This is the first correction, and then we'll get maybe further corrections. So at low energies, then what we expect is to have only the pure, this just gauge field, and this will confine. Okay. So this is a thing we expect to be confining. And indeed, the gravity solution is known for this case. The gravity solution is simple to find because it's basically the same solution we discussed yesterday. So yesterday we discussed the solution that describes the black brane, so the 3 brane at finite temperature. Okay. Because we have this Young-Mills field in 3 dimensions, and so the 3-dimensional Young-Mills, even U1 gauge theory, if you have monopoles, is confining. Okay, so furthermore reason this non-abelian theory is going to be confining. Well, yeah, the Young-Mills coupling grows in the infrared, but this doesn't yet tell you it's confining. This just tells you that you cannot analyze it. But yeah, to that level you see that interactions are getting stronger. Right? Okay, so now this is okay. What? Oh yeah, I was talking about the black hole solution. So we discussed yesterday a solution in Euclidean space where we had R3 and S1, and this S1 was some kind of cigar, right? This was the Euclidean black brane solution. And now we can get the Lorentzian space by changing time in these directions to R 2, 1. Okay. And one feature of this solution is that the work factor in these directions, indeed, well, here goes to infinity, and here is finite. So we have some W naught bigger than 0. So this has the features of this general discussion. So the solution somehow ends here. Okay. Now, okay. Now, one thing you can ask is whether this solution is really representing the same as 2 plus 1 Young-Mills theory. So here we can consider 2 theories. One is n equal to 4 on this circle, and this solution definitely describes that. It describes n equal to 4 on a circle. But on the other hand, we have the 2 plus 1 dimensional Young-Mills theory with no supersymmetry, just a theory with this Lagrangian in 2 plus 1 dimensions. So how well does that gravity solution represent this theory? Okay, you can ask this question. For example, if we consider the masses of blue balls that we consider that we compute using this solution, will they agree with the masses of blue balls we would find in this 2 plus 1 dimensional Young-Mills theory? Well, the answer is no, but we need to understand why. Why not? So the coupling in the 2 plus 1 Young-Mills is dimensionful, has dimensions of energy, as Gishe said. And we expect that the confinement scale of this Yang-Mills theory, well, will be of order this coupling, right? So this will be the lambda of this theory, the confining scale. On the other hand, the three-dimensional theory that we started with was compactified on a circle, and the theory really becomes 2 + 1 dimensional at energies which are much smaller than the radius of the circle. Okay? So we can think, from the point of view of the 2 + 1 dimensional theory, we can think of this 1 over the radius of the circle as some UV cutoff for the 2 + 1 dimensional theory. So above that energy scale, we have the 4-dimensional theory. Below that energy scale, we have 2 + 1 dimensional theory. So if we draw an energy scale, here we have 1 over R. Here we think we have 2 + 1 dimensional theory, and here we have really the 3 + 1 dimensional theory. Okay. Now we can compute this effective coupling. So this is just the 2 + 1 dimensional coupling constant, which is equal to chi square in 4 dimensions times n times 1 over R. Okay. This is just the formula that we find for the coupling by doing the dimensional reduction of from 4 dimensions to 3 dimensions. Okay? Is this clear? So one question. So we see that that for if chi square n is much bigger than 1, then this scale lambda. This scale lambda is much bigger than 1 over R. Okay. So we expect from the point of view of 1 dimensions, we expect the confining scale to be larger than 1 over R. Okay. So definitely, so we are above the cutoff. So the 2 + 1 dimensional theory will not be well described by this situation if Gn is much bigger than 1. It would be described if chi square n is much smaller than 1. This is the 4-dimensional coupling, I remind you. In that case, this scale would be here, okay? And then we start from 3 + 1, we go to 2 + 1, and then we get the confinement scale and so on. So if we compute blue balls here in this case, so if we take the 4-dimensional theory to be weakly coupled and we compute blue balls here and so on, then it would be a good approximation to 2 + 1. Up to a problem which, well, let me ignore this. But here we don't have this feature. Okay, so what we conclude is that, well, in this case, of course, the confinement scale, when we actually compute the actual confinement scale of this theory, it will be here of order 1 over R, right? So the mass of the Kaluza-Klein blue balls, the mass of the blue balls of this theory, that is the mass of the Kaluza-Klein states, will be of order 1 over R. Okay? And so this theory is not really pure Yang-Mills. Then you can ask, well, but maybe, well, okay, maybe we were not smart enough in finding a good example. Maybe there is an actual nice example where there is a gravitational dual of Yang-Mills theory. Now, suppose it had a gravity dual, okay? What is a generic prediction we can derive from having a gravity dual? By gravity dual, what we mean is some dual description where we have some geometry with a boundary, so something that has a boundary, and has some radius, at least the radius in the infrared direction, that is much bigger than the string scale. So this is something we need in order for the gravity description to be appropriate. So one generic prediction is the masses of, so here the masses of states will be, well, we'll have the lowest lying states, which will be some Kaluza-Klein states, living here at the bottom of this gravitational potential wall. And those masses will be much lighter than the masses of string states. Okay? Because if R is large, there will be a large separation between the masses of the gravity multiplet, of the gravitational degrees of freedom of the things that are massless in flat space but get a little mass because now they are in curved space. That mass will be much smaller, so the mass of the Kaluza-Klein excitations will be much smaller than the mass of the string states. Now, how can we generically distinguish between these two? I mean, if we are just given the spectrum of the theory, how do we decide something is a string state, something is a gravitational excitation? Well, one feature of string states is that you can have particles with spin bigger than 2. And so what you'll find is that the masses of states with spin bigger than 2 is much, much bigger than the masses of the lightest states. And the lightest, all the light states will have spin less or equal than 2. Now, we don't really know for sure whether n equal to 0 Young-Mills will have this property at large n or not. So whether just bosonic, ordinary bosonic Young-Mills has this property at low temperatures at low energies or not. But if n equal to 3 is similar to n equal to infinity, to the extent that n equal to 3 is similar to infinity, which to that extent, we can see that this is not the case, because in experiment we mentioned these Reshe trajectories, and the mass gap between the lowest state and further states along this Reshe trajectory is of order 1. It's not very different. Okay. So this the mass of the first excitation compared to the other ones that have spin bigger than 2 is not very different. So we don't have this condition. Actually, this mass is comparable. Okay. Okay. So that's this is one general feature. So whenever you read one of these papers claiming to have found the dual for Young-Mills, you should see how they avoid this problem. Yeah. Or you should read the fine print saying that it's not really the dual of pure Young-Mills, but it's the dual of some other theory that looks closely related to that theory. Okay, so now the last thing I'd like to do today is to say something about D-branes. So we discussed a variety of solutions that have some gravitational dual, and we started out talking about UN Young-Mills theory, or SUN Young-Mills theory, and those are theories that basically contain only closed strings, but we know that string theory also contains D-branes, so what is the interpretation of D-branes in the bulk from the boundary point of view? So we can have D-branes of a variety of dimensionalities, so we could have something like D0 branes in the bulk, D1 branes, and so on, up to, let's say, D5 branes in, so let's say in the 5-dimensional space, we could have up to D5 branes. Well, let's start with the D5 branes. So the D5 branes are branes that are extended all over the 5 dimensions, and in such a situation we'll have also open strings that live in the bulk, and so this is something we'll obtain. So this means that the theory will have extra matter in the fundamental or some small representation. So this represents the fact that we have extra quarks. Okay, so we have an SUN theory with quarks or with matter in the fundamental or something like that. If there are gauge fields that live on these branes, then those will have gauge symmetries in AdS. So if we have, let's say, NF D branes and we have a UNF symmetry on these branes, that will be a global symmetry of the theory. That means you have n quarks and we have some UNF global symmetry. Now, depending on the example, the symmetry could be different and so on. But gauge symmetries in the bulk correspond to global symmetries in the boundary theory. Okay? So here. Now, some symmetry, if you have a global symmetry in the boundary theory, that should be a symmetry that should be absolutely conserved in the boundary. It's absolutely conserved in the boundary theory. So it should be conserved in the gravitational theory. But the only symmetries that are conserved in the gravitational theory are gauge symmetries. So always global symmetries on the boundary should correspond to gauge symmetries in the interior. And well, finally, let me describe an example of D0 branes. So you can have D0 branes that are many things, but something that can be a D0 brane is a baryon in the boundary theory. Okay. Anyway, so that's an object that has tension mass of order 1 over g or 1 over n, or n, and so it's an object made of n quarks basically, and so that's this baryon. Well, I think I'll finish here, and maybe you can ask questions. Thank you.